Okay, are there any questions from last time? Today, I think we're going to try to do some of the more exciting stuff. I'm going to at least start contextual bandits. So I'm going to talk about how you use exploration for evaluation and optimization. And what I think this comes down to in practice is actually very simple. This is a graph from a paper that I had a long time ago talking about parallel learning. But the thing that I want to focus on is the y-axis, where you see the area under the precision recall curve. Now, this was about predicting the probability of click on individual ads with some big data set. And the relationship between the area under the precision recall curve and the amount of extra revenue that you get is very unclear. It's often the case that there are ways to improve the area under the precision recall curve without improving your revenue at all. You sort of get, the relationship between these two, I guess, is very loose.
Wait, so what are you trying to predict?
So we're trying to predict the probability of a click here.
Okay.
And we're using some algorithms, and we're doing it better and faster than people previously. We're evaluating against the area under the precision recall curve. And the degree to which the success here translates into actual revenue is very unclear. I think this is very often what happens in practice. You go and you optimize something which is kind of vaguely related to what you want, but it's only very vaguely related. And so you don't have a very good grip on what will happen when you actually deploy something in practice. Question?
Yeah. What does the y-axis mean, AURC, and also what is BFGS?
Yeah, so LBFGS is a learning algorithm. It's an optimization algorithm, I should say, which does an approximate Newton step. It's not important here because I'm not going to be talking about LBFGS. I'm worrying about the y-axis. So the y-axis is area under the precision recall curve. So this is a measure of the degree to which you manage to, okay, so you predict the probability of click for every event. You sort events by that probability of click. Then you kind of measure, it measures what fraction of the clicks are sort of on one end of the curve. So this is only weakly related to the quality of your predictor. And that's kind of a problem because this is a situation where people routinely do something which is very weak, and it's become institutionalized. It's a part of the culture of how people do things, and it's not necessary. You can actually have, the click lift, the number of clicks to the fraction of clicks be the y-axis if you do things right. So that's what this lesson is really about. How you make the y-axis be the fraction of clicks or the amount of revenue or whatever other reward you want to optimize. Okay, so let me give you some examples of the kinds of problems that I'm thinking about. One example is, say, news recommendation. So maybe a user comes to Microsoft, they have some history, Microsoft chooses to present some news story to them, and then the user is going to react to that. Maybe they click, maybe they don't click, maybe they click and then they come back immediately. There's many different possibilities. Okay, and now your goal is to optimize step 2. How do you choose what to present to a user so that they're most interested in it? And the thing which is challenging here is that if you show a news article about the Packers and the Saints, you don't have any information about whether or not I would be interested in a news story about the war in Ukraine. So it turns out that my wife is from Ukraine, so I actually am pretty interested in a news story about the war in Ukraine. But you don't. There's no way to get that information from a Packers Saints game, right? Okay, so this is one example. Another example is personalized medicine. this used to be theoretical, but we're actually now, I just came from a meeting talking to people about immunotherapy. We're thinking about how to use machine learning, maybe even these kinds of techniques in order to help solve cancer.
Are there any success stories of machine learning in medicine?
What's the question?
Are there success stories for machine learning in medicine?
I mean, the reason I ask is because this is one area where people would be super.
So we just had the machine learning symposium last Friday, and Suchi Saria came in and talked, and she has just rolled out a sepsis detector, which is used at Johns Hopkins now. Now, this is not quite a success story yet. So they believe this will be very helpful in reducing the amount of sepsis. So sepsis is a hospital-acquired infection where you get bacterial infection and your system shuts down and you die. If you detect that earlier, then it's much more feasible to treat it because you can throw in the antibiotics. But typically, the detection is very late in the process, and so when it's detected, there's about an even chance you die. So, and this is the number 11, I guess, that cause of death in the U.S. So this is a machine-learned system for trying to detect sepsis from various routinely gathered signals. Now, it's not quite a success because it just rolled out and they haven't, done a full evaluation of it. But they believe that it will be successful and helpful. Now, it is good to be, I guess, skeptical. Yes, skeptical about machine learning in medicine because the data tends to be extremely difficult to get access to, and very fragmented across different institutions.
Difficult to reproduce.
Yeah.
Because like private and you can't share it.
Yeah. Was there a question?
Oh, I was going to add to what you were saying about success in machine learning. So I think if you define success also to mean like to make healthcare more efficient, or like sort of inform policy to make it more efficient, there has been some successes as well. So one project that I worked on was like sort of a class of papers that came out saying that mammograph studies, like doing them as frequently as we do, which is like I think once a year is the recommendation. There's actually like not sufficient evidence showing that improves breast cancer survival. And so after this like large set of papers came out, basically arguing the same point, the American Cancer Society changed their recommendation from like once a year to being once every 3 years. And I think that saves a lot of money and minimizes stress and all these other secondary things as well. So
Yeah.
So that's another way in which I think machine learning has been helpful in medicine.
Yeah. So I think in general, machine learning is kind of nibbled at the edges, but I do believe there are really important machine learning problems there. And if we can reach a point where it's feasible to really pound on it, it can be very powerful. So what I'm thinking about here is a situation where, a patient comes to a doctor, they have symptoms, the doctor chooses a treatment, and the patient responds to it. And now your goal is to help optimize step 2, right? So this is the basic, why do you go to a doctor loop? And you would really like to personalize step 2. I guess when I was an undergrad at Caltech, the joke was that if you went to the student healthcare center, that there were 2 prescriptions they gave you. One of them is drink more water, and the other one is a pregnancy test.
They actually do that in Cornell. I have a friend. Actually, Randy is there. I mean, Randy is a male, and Cornell asked him, "Are you pregnant?" or something.
Yeah.
It's weird.
Yeah.
We can see you fine.
Yeah.
Okay, so the last category that I want to talk about is user interfaces. So there's a demo I saw inside of Microsoft, which is really fun, where somebody put one of these things on their head, and then they trained it using contextual diamond, which I'm going to be talking about, so they could type with their head. So somebody who is completely paralyzed could type. And that seems pretty cool.
So it's just a bunch of brain sensors that are measuring something around the brain?
Yeah, it's called a consumer grade EEG. It's the degree to which it measures the brain versus muscle twitches in your skull is not very clear. But it does measure something, and then something can be turned into a signal, which can actually type. Not very fast, but it can be done.
So you just think a sentence in your head and it types?
I think you're imagining something which is much more graceful than what occurred. What it's more like is you concentrate for 10 seconds and the character comes out. Right.
Okay. Then you have to solve a problem, then solve the problem for you.
But it did actually work. People actually could type with this. And I guess the key thing there is that you really need a learning user interface, because the exact place you put it on your head will change every time you put it on. Okay, so all of these we can think about. For all of these, we can think about the contextual diamond setting, right? So I'm going to think about a situation where repeatedly you see some context X. You choose some action A, and then the world gives you some sort of reward. So who has seen contextual awareness before? Fair fraction. Good.
Is there a need for the reward to be bounded by a 1?
No, not really. So we bound it from 0 to 1 in terms of the theory, but there's canonical transformations which allow you to apply the theory to any other bounded reward, basically. If you have truly unbounded rewards, then things start to break down, definitely.
Yeah.
And in general, if the range of rewards is very large, then things can start to break down.
When you have a minus infinity reward, you take it, you're done.
Well, yeah.
Can it be a continuous reward range?
Yeah, so when I say these brackets mean continuous.
I didn't see that.
Okay. Okay, so let's talk about the evaluation problem. So you have some policy. It maps features to action, so it's something that you can use in step 2. And the question is, how do you evaluate it? Right, so the approach, which essentially every internet company uses, is they deploy the algorithm in the real world. So this is typically done through A/B testing. You have your old system for doing something, you have your new one. You split the users in half get one, half get the other, and then you observe the outcomes. If you at Cornell want to do this, it's much more challenging, because first you need to found a company, and then you need to grow the business, and then you need to. It's extremely expensive there. A cheaper way to do it is you can go get hired at a company, and you can do it at the company. But nevertheless, this is obviously a very difficult process compared to what we're used to in most of the rest of machine learning. Nevertheless, it is a process which changes the y-axis. You actually measure the amount of clicks or the amount of revenue or whatever else.
I mean, the policy has to be deterministic, right? I mean,
no, it can be stochastic.
How would you train the probabilities based on
This is telling you nothing about how to train it. This is just given the policy, how do you know how good it is? Right? So I'm thinking about a policy which maps features to action. You can map features to a distribution over actions too that you draw from. That would be fine. If the policy is non-stationary, then it's going to get much more difficult. Right? So we're not going to talk about non-stationary policies today. I think we'll do that next Monday.
What do you mean by non-stationary?
So it will turn out that your best exploration algorithms are non-stationary, since they narrow in on the best choices. So that means that the mapping from features to distribution over actions is changing over time. And so evaluating a non-stationary policy is substantially trickier than evaluating a stationary policy.
And the policy will depend upon the history, basically.
Yeah.
I have a question.
Yeah.
So for the reinforcement learning that we're doing, is it a similar setup to that?
Yeah, let's go back. So this looks like reinforcement learning, and it is a form of reinforcement learning. But I mean this in a more limited sense than full reinforcement learning. So in full reinforcement learning, what happens is you have the same kind of loop, but now the reward can depend upon the previous T actions.
Ah, right. So that's some memory. This one.
Yeah. So we're thinking of a situation where there is no memory, where the reward is associated with that action in that context. Right? And it makes a huge difference as far as how tractable things are. So if you want to deal with a full credit assignment problem, which is what happens when you want to know which action led to you losing the game, or which action led to you winning the game, and how you should blame the different actions in terms of your overall performance. That becomes so what do we know? In limited settings, we know how to solve this. If we have an MDP, we know how to get some solutions. There's some very new papers, which maybe we'll talk about towards the end of the class, talking about how to do this with generalization. But in general, little is known in terms of the theory of where that's tractable. And then in terms of what's done empirically, it tends to be things with enormously high sample complexities. So if you go and you look at like Atari DeepMind, they play Atari. The system is essentially playing Atari for 100 million frames or something like that. So it's very inefficient in terms of the number of samples, which makes it very difficult to apply in the real world. Here we're trying to look at systems which can be applied in the real world. So this is the claim is that contextual bandits are a specialization of reinforcement learning, which is routinely tractable in the same sense as supervised learning is routinely tractable. And so that makes this a useful subproblem to think about. And then in situations where you can come up with an immediate reward that makes sense, you can think about contextual bandits. Situations where you cannot, you're on more of an adventure and you need to think a bit harder.
I mean, would it be right to say that CB is a one-step ahead?
Yeah. Okay, so let's talk about what people do at companies when they are faced with these problems. They do something which I'm going to call the direct method. So they use the past data to predict the reward given the features in the action. And then the policy that they're making is implicitly this argmax. So you choose the action which has the largest predicted reward. Okay, so this is commonly employed. It also does not work very well. There's a simple example which kind of shows why this fails. Okay, so we have two actions, A1 and A2. We have two features, X1 and X2. And now, let's say that in our observed data, A1 was played for X1 and A2 was played for X2. Right? And when A1 was played for X1, the fraction of, let's call them clicks, was 0.8. While when A2 was played for X2, the fraction was 0.2. So then you can form your reward predictor and you can apply it, and a very reasonable choice would give you something like this, where it's 0.8 and 0.2. So you're predicting perfectly on your observations, and then it's 0.5 in between, right? So then maybe you deploy this, and you observe that when you play A1, so the predicted reward on A1, given X2, the predicted reward for A1 is 0.5, while the predicted reward for A2 is 0.2, so you'll play A1. So then maybe you observe 0.3 when you play it, and maybe you retrain, These are actual numbers that you get when you retrain with a particular representation. But the point is that things stabilize. You're now always going to play A1, and the truth might look like this. So the truth might be 1 if you played A2 on X1. So the core issue is that, well, you don't have the information you need to learn. So you never observed what happened when you played A2 on X1, and so you never build a policy which could take advantage of that. Okay, so are there questions about this example?
So you can try to solve it with A/B testing, right? By A/B testing, you will be able to perform both X1 and like A1 and A2, right? But it is very expensive.
Yeah, so you can do A/B testing. When people use A/B testing, they typically, at companies, they typically mean something a little bit different from what I'm saying here. They typically mean you partition the users in half, which implicitly partitions the events in half. But it means that users would be exposed to A2 or to A1, not to a mixture of both. However, you may want to be randomizing on a per event basis rather than on a per user basis. And then, yeah, so things are a little bit different then. Because an individual user may see both A1 and A2 and may have a chance to react to both of them.
I mean, if there is no visualization in the reward function, there could be an action for a given state which has a very high reward that you will just never explore. So wouldn't it be like the worst case you have to like go apply all the actions for all the
Yeah, so I think one question is, what do you compete with, right? So if we go back to the contextual diamond formulation, we're trying to learn a good policy for choosing actions given context, right? So there's a set of all possible policies, which may admit very unintuitive possibilities. But there's also, but that's not what we do in supervised learning. In supervised learning, what happens is we compete with some set of predictors, right? So all decision trees, all depth 3 neural networks, all linear predictors, right? So those are the sets of policies that we compete with. And I think the idea here is that we're going to compete with a set of policies in the same sense.
No, I think the question that I'm asking is like, so there are problems that are interest in AI, in which there's some kind of generalization. So if there's a given state which has some kind of an action which is suitable, and any state which is similar to it will have the same action which is suitable, or like, still there's some kind of generalization in state space. If you assume a worst case scenario, you can have a state for which there's one action with the highest reward that you will never get unless you actually try it, which means you have to try all the actions for that given state. And so if you do some kind of a tabular learning, you'll have to, and in the worst case, do it for all the states X and all the action states. So
yeah, so tabular corresponds to a super rich space. So if for every X you did a test of A1 and for A2, and for then you could form out that tabular solution. But I think typically we're going to imagine we only ever see an individual X once, and then it becomes not possible to just fill out the tabular thing. You have to actually think about a policy class and ask which policy in this policy class gives you good performance. And then because you have a policy class, that policy class is not fully expressive, there's some bias, you'll be able to succeed with a much smaller number of samples.
But can you be optimal in like sample complexity less than the search space?
Less than which search space?
Number of states, time over actions.
Yeah, so then when you say state, you mean X.
X, yeah.
So I'm typically thinking of X as a context. So okay, so let's talk about state for a minute. State is a very loaded word. It has a lot of different meanings. So generally, I think we should avoid it.
Okay. I meant like space generating the space from which X is generated times the number of actions.
Yeah. So I'm going to be talking about methods which have no dependence on the size of the space generating contexts. So we're going to have a dependence on the number of policies that we compete with, but not on the number of possible contexts.
So I had a question. So when Dipendra was asking, I was thinking maybe because in this example, you don't explore it on X1 because like you put that, okay, since we didn't explore it, it has 0.5 reward. So, and 0.8 is obviously greater and hence we always play with A1 on X1, right? So, what if we, like, I don't know what the true one was. What if the true one was 1 on A2 and then, yeah, it is 1. So, we have to put a higher cutoff. Like, I'm saying, so if I'm very strict with giving estimated rewards, I just give it 1 or whatever I didn't explore, then I actually force my iterations to choose that reward to get a better estimate or something. So that is, I think, what you call, what are you competing against? So here I am just raising the bar against what.
Yeah. So you're thinking about an exploration strategy. So you're thinking about optimistic initialization as an exploration strategy. Now, it has a bit of an issue in this case because it's usually thought about in a tabular setting, and we're going to have no dependence upon the number of possible x's, which means that we can't really afford to have a tabular setting. So it's hard to use this strategy. But in general, I'm not trying to address what is a good exploration strategy right now, because it's going to take more time than we have. We'll talk about that next time. Yeah?
Just one more question. So if we would imagine that we were in a Atari game,
Yeah.
then we would explore all of them because we can go back to the previous context and try A2 and right. So it's like because right now we can explore A2 because when we explore A1, that's it. So it's like the state is changed.
That's right. Yeah, so in the actual Atari game, you can scroll back, and that is a very powerful strategy, which people consider cheating, I think.
Yeah, we can take chess and we can make a tree.
Right.
Okay, so one claim here is that generalization doesn't work. So many people who are used to supervised learning are used to thinking about generalization as being the answer to everything. And generalization alone is not successful here because we generalized well, we could actually predict our observations, but that was not adequate to get a good policy or the best policy. It can help, and often it does help to some extent, but it's just not enough. Another is that you really need to be doing exploration. So A/B testing is kind of the right instinct, but there's a little bit different style of exploration, which I think gives you something better. And then the last thing is that, well, it probably doesn't apply here, but I've talked to people who think that, oh, well, the learning algorithm is going to mess up sometimes anyways, that's exploration. But that's not really what I mean by exploration.
So the fact that generalization is insufficient, that's an empirical. It's not there's no proof. I mean, it really depends on the model that you're using.
So no, there are lower bounds for contextual bandits, which essentially show that generalization is not enough.
Mm-hmm.
You really need to do exploration to succeed.
What is generalization?
So that was from the first lecture.
I forgot.
So you remember the sample complexity of the first, sample complexity part of the first lecture? So generalization to me means competing with a policy class. So you want to compete with the best policy in a set of policies. And I think if you use that definition, you'll find that it generalizes. It's a generalizing generalization definition.
I mean, no, but there was a meaning to generalization in terms of like the training data. So you have as samples, and you have some bound on the generalization error in terms of these samples.
Yeah.
Here, what you have, you don't have a training data. So is it based on the samples that you see during, like during exploration, or I mean, I don't know.
So there's several different ways you can think about generalization. One of them, the fundamental ones, used to be competition. So you're competing with a set. So there you're competing with a set as well. You're saying that, oh, I can pick out the best classifier in my set, and that will actually be a pretty good one on the test set. Right, so think about using the Occam's razor bound. Given the Occam's razor bound, you have that logarithmic dependence upon the one over the prior of an individual hypothesis. So you have a dependence upon the description length of the hypothesis. So it's the description length of the hypothesis divided by the number of samples, which controls the gap between the empirically observed error and the true error. So that means you can choose the hypothesis, which minimizes the lower bound, or doing error rate. So it minimizes the upper bound on the error rate, and then you can be sure that that will actually give you a pretty good hypothesis on the test set. So then an entirely different notion, then it has to do more with adversarial learning. So in adversarial online learning, you have a set of different experts, each of which is making predictions, and one of them will be better than others, and you want to make sure that you're near to its performance. So the protocol is a little bit different. You're not, and the assumptions are a little bit different, but you're still competing with a set, or you have the capacity to compete with a set implicitly. Okay, so this is the direct method. This is what everybody uses by default. It's kind of problematic because it doesn't handle exploration, and it leaves you in the offline setting with the end of the precision recall curve kind of y-axis. So let's talk about the importance weighting trick. Okay, so this is the simplest way to get a different y-axis offline and actually optimize directly against what you care about. Okay, so let's imagine that we've collected T exploration examples. So an exploration example consists of the features, the action, the reward for the action, and then the probability for an action. All right, so that's good. And now we want to try to evaluate a policy. And so what we're going to do is going to compute an empirical average of this formula here. So we have the reward times 1 if the policy's action equals the random action, and times 0 otherwise. And then all of that is divided by the probability of an action.
How do you get the results?
What's that?
How do you get the results?
Yeah, so when you're collecting the data, the idea is that you're randomizing over the actions. So maybe you're randomizing per event rather than per user. So you randomize for each event, you have some distribution over the actions, you draw from that distribution, and then you record the probability of the drawn action.
So in terms of like website like commercials, so the probability is like when the user will click on the advert, probability is to show that over the ad.
So it's the probability of the action, not the probability of the response, right? Because
Action is showing
the commercial or the news story or whatever, yeah.
So this requires the same exploration strategy to be used for the entire sample. And generally, like the policy evolves, so policies are non-stationary.
Why does it need the same exploration strategy?
I mean, so there is an exploration policy which is generating the sample. This cannot change for these key samples that you have. Like, it cannot be like.
There's no restriction here. So the distribution over actions can be changing from event to event. As long as you record the probability of the action, this will work out.
I mean, when you do the important sampling, you have a queue, which is the exploration policy.
Yes.
And then you divide by the queue, and then you take some samples from the queue. But you cannot have multiple queues, right? I mean,
so for every event, you'll have some condition on everything that's happened in the past. You have a distribution over actions. You'll draw from that, and then you'll record the probability of the drawn action. And then for the next event, you may have a different distribution over actions. Is that clear? Is the definition clear, at least?
I mean, I understand what you're saying, but I mean, I'm not seeing how the maths gets you this. But maybe I need to.
Okay, well, let's go on because we're actually going to prove it. Okay, so the claim is for any policy, for any distribution D over the X and the R's, the value of pi is an unbiased estimate of the expected reward. And you can also bound the deviations, which is a bit more involved. So in terms of the proof, what you can do is you can condition on the X and the R vector. So the only randomization left is the randomization over the action. So you have the expectation over the action of that thing inside of the average. And then you can say, oh, look, the expectation is really the sum of the probability times the thing inside. And then you can go, all right, so the probability is going to cancel, which is why we had the probability on the bottom. And then the sum and the indicator function will cancel, which leaves you with just the reward of the policy's chosen action. So this is unbiased on a per event basis, which means that it will be unbiased for a sequence of events as well. Okay, so this is a very simple thing, but this is very important because this says that the y-axis can be revenue or clicks or something like that.
In the deviation bar, what is T? It's the number of samples.
It's a number of samples, yeah.
And P by X is the probability.
Yeah. So you have. So when I say P sub pi of X, I mean the probability of the policy's chosen action conditioned on X. Right. So if the probability is chosen, if the probability of the action becomes too small, this is going to blow up, right? But if it's something like uniform, then this is going to be something like the square root of a k over t, where k is the number of actions.
It's like square root in number of in the action space.
Yeah. So since it's k over t, it's like thinking, so it's like 1 over t over k, which is like saying your deviations are kind of like what you would have if you had just t over k samples and it was a supervised setting. So the number of actions is compared to the number of events in a ratio. So this is like saying the deviations in this contextual diamond setting are similar to supervised learning with a factor of number of actions less events. Okay, so let's go through an example. Suppose that we have 2 actions, 1 and 2, and the reward is 0.5 and 1. So the probability of the actions will be 1/4 on action 1 and 3/4 on action 2. Then when the 1/4 action is drawn, using that estimator, we get 0.5 divided by 1/4, which gives you 2, or 0 because the indicator function is 0 for the other action, right? And then when the 3/4 event happens, you get 0 for action 1, and you get 4/3, which is 1/3/4 for action 2. And then if you look at the expectations for that, it works out to give you the right value. Okay, so that's fun. It's maybe the most important part of this lecture. You can actually change the y-axis to be something useful. The next thing is also very important in practice, which is how do we actually do better? So it's often the case that there's some reward estimator that you can form. And while we were saying the direct method is kind of bogus, having a good reward estimator can obviously be very powerful. We'd like to take advantage of that as much as we can. So there's a trick here, which is pretty nice. You can change your estimator to look like this. So if you were just going to estimate using the reward estimator, you'd have the last term. You'd have the estimated reward of the policy's chosen action. But we want things to be unbiased. So we'd like to have the reward divided by the probability of the action. But now because we're adding on the r hat, we need to subtract it off as well. So this is the way to kind of, you add on and subtract off the r hats. And now what do we gain? Well, if r hat equals r, the first term is 0. And the second term is the only one which remains. So that means that if we can predict the rewards perfectly, we have a huge win. Because, I mean, essentially the reason why we had that k dependence, depends on the number of actions in the deviations, was because we were dividing by the probability. If this term goes to 0, all the variance from that first term goes away, and then it's a win. Okay, so what can you prove about this? So if you have a reward estimator and it has some deviation from the truth, and if you're estimating probabilities and it has some deviation from the truth, then what you can prove is that for all policies and all events, the deviations of the value estimate from the expectation are bounded by big delta times little delta. And that means that if big delta and little delta are less than 1, you win, right? Because you're multiplying together deviations, and if they're both small, then you get something even smaller. So I'm typically thinking about a situation where little delta is 0, so then you're unbiased, and then the right-hand side becomes 0. But even if your probability estimates are off for some reason, you can still use this kind of technique to improve over naive approaches.
I mean, what are the reasons why you won't be able to have the exact probabilities? Like, why? I mean, you generally know the exploration policy, right?
Yeah, so when you know the exploration policy, I think it's all good. It's when you're trying to do exploration scavenging. So somebody in the past explored, but they forgot to record the probabilities, that you start running into situations where you have these p hats. That's part of it. There's another part which is, so if you have so some exploration algorithms are better than others as far as producing information. So if you're familiar with an upper confidence bound style of exploration, so you choose the action which has the largest predicted reward, for example. or something like that. And then you update the policy, and then there's a different action with the larger predicted reward. So the action is formally deterministic at every individual event. But if there's some permutability of the events, there's a distribution over actions that's implied by the changes in the policy. So you can define a new probability of action, which is the fraction of the events for which a randomly chosen policy from the sequence of policies would choose that action. And then you can form a new probability based upon that. It's complex. Let's not do that.
So the reward estimator is because you can't observe the reward?
You do observe one reward, the reward for the chosen action, but you don't you don't know the true expected reward for all actions. So the second R hat term is the reward for whatever action is chosen by the policy.
For the chosen action.
So you have the exploration policy, which gathers the data, and then you have the policy pi, which you're trying to evaluate. These may not choose the same action. And so the R hat of pi of x is necessarily some approximation, because the action that pi chooses may not be the same as the action which the exploration policy chose.
So what is also the?
That's the observed action reward for the exploration policy's action. So the first term is only non-zero when the exploration policy choosing A and pi of x choose the same action.
So then why do you need an estimator? You were told it because that's the word was taken.
Yeah, so I mean we can certainly go back to
That'll be the direct method.
we can go back to this if we want to. And that's fine. I mean this is unbiased. It's just that it has potentially large deviations. So we would like to reduce the deviations, and one way to do that is with a reward estimator. So if the reward estimator predicts the value of the reward perfectly, the first term becomes zero always, and you're only using the second term. Okay, so let's take a look at things. Okay, so here's a data set, which is like, it's derived from the RCB1 data set that I showed you last time. There's a different kind of label information here. So there's the chosen action first, which is either 1 or 2, right? And then there's, okay, so it's a loss rather than a reward. So it says the loss is 1, and it tells you the probability of that action being taken. So the way that I generated this data set was I just ran through the RCB1 data set, and with probability 0.5, I said, oh, I'm testing action 1, probability 0.5, I'm choosing action 2, and then I checked to see what the loss was for that action in order to generate the loss value, right? Okay, so this is a reasonably large data set. Let's see. And now, what I can do, okay, so I can say, okay, I'm doing contextual bandit learning. There are 2 actions. The way I'm going to estimate things is with the direct method. This is the data set, and I'm going to allow bigrams, and I'm going to allow up to 4 skips between the different elements of the bigrams, and I'm going to use a hash function with 24 bits, and I'm going to tune the learning rate just a little bit.
What is the method for approximating the reward?
So I'm actually recording, everything works on a cost basis here. So the cost is 1 if the action is not the label, and it is 0 otherwise. So you can run through things. This is a little bit slower than what you saw previously because there's a bit more work going on under the hood. But so you can use progressive validation in the same way as we discussed previously. And you can see that the error rate ends up being relatively small. Now this is the direct method, which I poo-pooed earlier. So why is the error rate small here?
I mean, your T is very large.
My T is large, yes, but I argue that generalization was not sufficient previously. I said that you can't succeed no matter how much data you get. So why does it work so well?
Your reward can only take 2 values, right? 0 and 1.
That's true.
It might be easy to guess what value.
Yeah, so but we're not taking advantage of that here. There's the learning algorithm is just operating. It builds a reward predictor for each individual action independent of the other.
Yes, I mean, direct methods is worse when your reward approximation is pretty bad.
Yeah, that's true.
So if you can, I mean, maybe in this case, the reward approximation is working pretty well. So
yeah,
just like doing a summation.
So that's part of it. There's another really important point here, which is, although we're not, you have the best possible kind of exploration data here, essentially. You have uniform random exploration data. Maybe best possible is the wrong term. You have high quality exploration data here.
Which is uniform.
Which is uniform. And that means that all of the possibilities have support. So there's at least a chance for any action in any context. And so the performance is actually pretty good. So you can switch this. You can say, okay, we'll do IPS. So this is the inverse probability or inverse propensity score. So this is using that first formula, which allows you to have a y-axis, which is the actual loss.
So in the normal like scenario, you won't have this much like uniformly distributed data, so you can get the result.
Say again.
In every scenario, when you want when you would apply this algorithm to data, you won't get the uniformly distributed data.
Yeah. So typically, it would not be uniformly distributed. And next lesson, when we talk about exploration algorithms, we'll see that the direct method can break down. But because we have such high quality exploration data, it's actually working very well here.
It's actually very surprising that uniform sampling is working so good. I mean, generally you use like something more sophisticated. I mean, in the RL you use like epsilon.
Well, the reason why you use something more sophisticated is because you don't want to incur loss as you're gathering the data. Right.
Is it actually, you don't know that it is not uniformly distributed in the real life scenarios, or do you have to prove it somehow? Like how do you know that it is uniformly distributed or not?
So the key thing is when you're gathering the data, you want to create a distribution over actions explicitly. So you say the probability of action 1 is 0.5, the probability of action 2 is 0.5, and then you draw from that.
And they usually we don't know. It's not exactly.
Depends on the scenario. So one of the things that I've been working on is deployable contextual bandits. So later on, I'll show you it, but there's a website you can go to right now, and you can say deploy, and it will create an instance of a system for contextual bandits in Azure. And then the way the system works is it explicitly creates a distribution over actions. So you have an explicit distribution, it draws from that explicitly using a pseudorandom number, and then it records the probabilities appropriately.
I mean, just a sanity check. If we knew the policy you were trying to evaluate, then there would be like no point to use anything other than the policy itself for sampling, right? I mean, then you wouldn't care about like support.
That's true. That's true.
It might be better to use the important sampling policy for pi, like a policy that gives propensity proportional to pi times delta. Like to be absolutely efficient in terms of values.
I see. I think I know what you're talking about. Let's go back here. So where to go? There it is. Okay, so instead of using this indicator function, you can use the probability that pi chooses the action A. And that is correct. So that's a way to lower the variance a little bit further. Yeah. All right, so this is the double robust. So there's not very much difference between these. All of these are giving very good numbers. So if you recall if we use the same kinds of parameters in a fully supervised setting, the average loss was about 0.045 or 0.44, something like that. So it's just slightly better. So this is kind of an illustration that it's possible to learn from this data fairly effectively. Okay. So I forgot to tell you how this works. So we're going to use a reduction. So we're going to reduce to constants of classification. And when I say reduce constants of classification, I mean a very particular problem. I mean, suppose you have a distribution D over features and a cost, 1 per action. And then your goal is to find a classifier which minimizes the expected cost of the chosen action. And so we have this expectation over x and the vector of costs of the cost of the chosen actions according to the hypothesis H. Okay, so this is like a fully supervised version of the same problem as in contextual bandits, because you have the cost for each action rather than just having the cost for only one explored action. And then you can map the contextual bandit data into the cost-sensitive multi-class classification data using this kind of mapping here. Right? So you can say, for action A prime, so you start with a X, R, and P, and then for action A prime, you're going to say that the reward is the double robust estimate. And then you negate that to get the cost. Is that mapping clear? So the features map to the features. And then for every action, A prime, we have to create a cost. The way we create that cost is by using the double robust estimate. And then the reward estimate can just be formed in some sort of essentially an arbitrary fashion, but inside of VW, it's being formed by building a regressor and just kind of predicting in a relatively naive fashion. Okay, so I just showed you these examples running. So the double robust, if you tune the learning rate, performs slightly better than the direct method, but not very much. It's very similar. The inverse propensity score is a little bit worse.
That's surprising.
Yeah, so I think the additional variance matters quite a bit, basically.
I mean, generally, I used to think like direct method was strictly worse than both the DR and IPS.
It's not always true. The variance can really kill you. So I think it's often the case that variance matters more when you optimize than when you evaluate. So we're talking about optimization here. We're doing the learning as we're running through the data. And the variance screws up the learning process even more than you would expect from the widened confidence intervals in evaluation. Okay, so here's some experimental results that we did in a paper a long time ago. It shows that the double robust method is robust. I don't say. So the green, we're trying to get our error as small as possible. The green is the double robust. Typically that's smaller, although not quite always. There's the IPS approach, which is the red, and it suffers from a lot of variance, as we were discussing. There's also this offset tree, which is a different approach that I'm not talking about right now. It has some nice properties, but it isn't as low variance as double robust. So in most cases, double robust works better than the offset tree. Okay, so that's not quite it. There's another trick inside of EW, which is essentially involves reducing to a different based learning algorithm. So instead of reducing to cost-sensitive multi-class classification, you can reduce to importance-weighted multitask regression. So what is that? So let's think about a distribution over a quad where the first element is the features, the next is an importance weight, the third thing is a cost, and the fourth thing is an index. And now
I mean, is W a constant?
W is something, no, it's something which is drawn for each event. So the idea is that you're doing regression, you're trying to predict the cost, but there's an importance weight, and there are multiple tasks where the task is what that I is indicating, right? So a different task for each action, essentially. And now you can map the contextual bandit data, XARP, into the importance weighted multitask regression data using this mapping here. So the importance weight becomes 1 over P, which allows you to do an unbiased estimate of the squared loss. And then the cost becomes negative reward, and then you just have the action. Okay, so this is helpful if you use MTR to do multitask regression. That gives you good performance here. It's particularly helpful in terms of computation because you're sort of only updating for the action that you took and not for all the other actions. So if you're doing the cost-sensitive multi-class classification, you're specifying a cost for every action, and that cost is unbiased. That means that you're updating for every action internally to the system. Here, you only really need to update for the one action that you explore. And then the other thing which is nice here is that the range of the costs is exactly the same as the range of the rewards. If we go back and we think about the range of the costs implied by the double robust estimate, that range may be larger than the original range of the rewards, which is nice in terms of a more canonical system. Okay, so I don't know a good analysis for this trick. It's clearly unbiased, but I don't know a good analysis for what its variance is. And it does work very well. So between multitask regression and double robust, I think it's essentially empirical. Which one gives you the best performance?
But in the case where you know the exploration policy, can you just like stick with the direct method and use it?
So this is almost sticking with the direct method here, because we're building an estimator of the reward or the cost, right? It's just that we're unbiasing it. using that 1 over P.
Okay, yeah. I mean, but in the case of like W robust, I mean, like, there wouldn't be any point using the W robust if you have the same exploration policy as evaluation policy.
Yes. I mean, if the policy that you want to evaluate is the exploration policy,
Yeah.
then you can just compute the
Monte Carlo.
average reward observed over time.
I mean, is there like, I mean, this.
But almost always that's not the case, because you're almost always asking what would happen if I had used a different policy.
That's.
Right? I mean, the point of offline evaluation is to try out new things, not to try out old things. Almost always.
Question? You mentioned the potential issue if the direct method maps like data to a different range than the actual range of rewards. Is there something in the regression that makes sure that doesn't happen, like a norm constraint on the direct method, or is there like some computation or clipping?
So I wasn't talking about the direct method. I was talking about the double robust. So if we go back to the direct method is just predicting the observed rewards directly, right?
Okay.
So there's no change in the range there.
Okay.
But there is a change in the range for double robust, because so suppose that our hat is, or for IPS, let's just go to IPS. Right. Okay, so let's look at this. So suppose that P is 0.5 and the reward is either 0 or 1. Then the value of this term is going to be either 0 or 2. Right, so the range is kind of blown up by a factor of 1 over the minimum probability. So it's kind of awkward, and that's the source of the additional variance, which can screw up IPS. Yeah, so that's not entirely satisfactory, and yet still, the fact that we can make the y-axis be the revenue or the clicks or something is amazingly useful. Okay, so the last set of algorithms that I wanted to discuss is you can essentially apply any reinforcement learning algorithm. So Dipendra recently did something applying a policy gradient algorithm. I don't want to go into all those algorithms because there's quite a number of them in general, but that is a class of algorithms you can apply in this setting, of course. Okay, so here's a summary. You can deploy things. That's called A/B testing. That's the standard way to evaluate in practice at real companies. It's the gold standard for measurement, but also for cost. You can use the direct method, and that's often what's used in practice. That's where you get area to the precision recall curve. It obviously has some value, since the generalization often does help you lead you to somewhere better. But I think typically you cannot achieve the best performance using this approach. You can use this kind of inverse probability approach. You can use double robust. You can use multitask regression. I guess I should also put you can use any reinforcement learning algorithm in general. So are there questions about this?
So I got confused in the middle by, like, were we switching between learning and evaluation, like every now and then, or was it like just to, like, so you said use any reinforcement learning algorithm. So, like, how does it give us an evaluation of?
Yeah, so we're switching right about here from testing things to training. So there's a set of techniques for testing, which I think are very important. They're probably more important than training in some ways. But then there's a set of techniques for training, and they have some overlap, but the overlap is not complete.
Yeah.
Right? So you can use so multitask regression is an example. So you can You can do the multitask regression for training, but it does not give you an unbiased way to estimate the value. So if you want to do unbiased value estimation, then you want to be thinking about things like double robust and IPS.
And WRS doesn't give us a way to learn. It was there.
It sort of does if you go here, because you can use double robust to fill in the costs for all the different possibilities in an unbiased way. But there's a step there from, oh, I can estimate the value of each action, to, oh, I can train with that.
I mean, basically, like you compute the objective using WRobust and then do gradient descent.
Yeah, yeah.
Or whatever optimization was.
Yeah.
It's just very, very curious. Why would you ask the question that how good would this policy do when you're ultimately interested in what's the best policy? Like, if I can give you like the best policy, you wouldn't even care about policy evaluation, would you, right?
I think that.
Like, I mean, how does it work in that?
So how do you know you have the best policy?
Fair enough. I mean, but the algorithms show you like you're doing descent over objective. So.
Yeah, so I think the problem in industry is that everybody says they have the right approach. And so the person who has control over things is like, okay, prove it. Now, often that proof, it comes through an A/B test.
I mean, even
But being able to evaluate things offline is enormously helpful.
But even this is like approximation in a way. I mean,
This is an unbiased estimate of the value of the policy if it had been deployed at the time that you collected the data.
sure.
Right? So that's it's not perfect as far as predicting what will happen in the future, but it's pretty near. It's about as good as you could hope for from data collected in the past. Okay. Any other questions? All right. Thank you. See you next week.
Michael,
Yes.
thank you for that, right? So,